I'm Shailendra Kadre, and I'm your host today, host and instructor for your today's training course. So today I will give you one assignment actually. So before that, we'll revise what we did in the last lecture. So if you see this PPT which is there in front of you right now, on the right hand side there is something covered like what is comes under syntactic analysis and what is covered under semantic analysis. So under syntactic analysis, two main topics are stemming and lemmatization. So stemming, I think stemming and lemmatization, you are already aware. So once again, I will take you to stemming and lemmatization. So stemming and lemmatization. So stemming and lemmatization, one thing, and then it ends with the syntactic analysis ends with part of speech tagging, which we call as POS tagging. Okay, so I want to tell you like difference between stemming and lemmatization. So you can observe that left hand side transformation, whatever we have done, we have just removed the suffix ing, es, ed, er, and just got the root word. So root word is converted as chang. So I think chang has no meaning in proper English. Chang might be a Chinese name or something like that, but it has no meaning in English language. So whatever we have done in the left hand side by just removing the suffix, that is nothing but your stemming. So as you see, stemming can reduce to a root word which may not have any meaning at all. But still we work with it and we use it for normalizing our text. So suppose if our text document is having changes, changed and changed, all this kind of transformation of change, then we uniformly reduce it to chang, C-H-A-N-G, chang. Only remove the suffix and keep the word. So even if it is not having a meaning, we keep it. So this is called word transformation and this is called normalization of the text. So we are changing all these forms of change into the base word, which is chang. Okay, so there is stemming. But if we are interested in proper analysis, not only we change the suffix, but we bother to keep the meaning, root word, whatever the proper root word in English. So we bother that that after transformation, after normalization, the word comes into proper form. So change, changing, changes, changed, and changer. So they are properly changed into a proper English root word, which is called change. So change is definitely having, as you all know, change is definitely having a meaning in English. So lemmatization will do a proper job. But the con side of like the negative side of lemmatization is that the stemming, as you can see, is very fast. Just remove some suffix, and it quickly does quick and dirty job. But lemmatization means you need to really search for the real root meaning in the dictionary and then put that particular base word for all these transformed words. So it needs more memory and more computing power. So now it's up to you, like what kind of analysis you would want to do, what kind of computing resources, and what kind of project time is available to you. So based on that, either you will go for stemming or lemmatization. Okay, so these are the two things in stemming and lemmatization. So these two headings like stemmings and lemmatizations are two main parts of any syntactic analysis. So you see here on the right hand side, syntactic analysis, stemming and lemmatization, just now we saw. After that comes something called part of speech tagging. So part of speech tagging is nothing but your POS tagging. Okay, so it is POS tagging. And POS tagging means like you give a proper functional form to a particular word. So either the word can be a noun, word can be a verb, it can be adjective, it can be an adverb. So a more complete list, like it is mainly around, these are the main parts of speech tag, main categories: noun, pronoun, verb, adverb, adjective, proposition, conjunction, and interjection. So these are the main categories under which part of speech tags are divided. So in the last class, I had suggested you to Google out all these what POS tags which you are not aware and find out what is its meaning in English. So mostly many people might have some confusion in what is conjunction, what is interjection. So these things you need to find out in Google. These are basic grammar forms which we used to learn in our high school English and all that. So I'm keeping it out of scope for this class. So you better Google it out and check once again. So a more complete list of part of speech tags is given here, and left hand side is their abbreviations. Like CC is coordinating conjunction, CD is coordinating cardinal number, DT is determiner, then JJ is adjective, then VED is verb past tense. Then like that you can see. I'll stop a minute here, and I will allow you to have a look at the tag and its description. So these are the basic tags which are used by CMU tagger. CMU tagger uses that. So CMU tagger uses that means there are different kind of tagger tools available in the market. So some different tagger tool might have different kind of abbreviations for the same adverb and same noun verb and those kind of things. So it may vary from tagger to tagger. So for one particular tag uses this particular 37 part of speech tags. So you can see, spend a minute and have a look at what is there on the screen. So in which if you see main things are RP is particle, then VBD is verb, then verb in past tense, then you have JJ as adjective, then you have NNS means noun plural, NNP means proper noun singular. Similarly, you have different tags for different part of speech tags. So these are the right hand side description is nothing but the function of that particular word in a sentence. Okay. So now if we go to the example, so this is the example given. Verb is sentence is I want an early upgrade. So this is this is a proper sentence which maybe a person is talking to a chatbot or any speech recognition software which is dealing with either hotel reservations or dealing with airline ticketing. So these kind of sentences are very common there. I want an early upgrade. So if you want your chatbot to understand this, you should be getting this kind of a POS tagging analysis. So I is pronoun, want is verb, and N is a determiner, early is an adjective, and upgrade is a noun. Okay, so that's what is seen. And the same thing like if we see in the form of a different sentence it is a different sentence, but now it is done in the form of tags or coded tags. So she sells on the seashore. Okay, little tongue twisting kind of sentence. So you can see how the tags are given. So NNS is your NNS means noun singular, noun plural, and seashore is a noun, a proper noun. D is a determiner, and PRP is probably preposition. So like that, you will get out of your part of speech tagger. So this is the very much part of your syntactic analysis. Okay. So syntactic analysis is the end result of your syntactic analysis. POS tagging is the end result of your syntactic analysis. So two main things, stemming and lemmatization you understand very well. And now you understand what is part of speech tagging. So now you will ask me a natural question that why in NLP we do part of speech tagging. So today we got some useful material on that. So even if you be doing some kind of lemmatization, so lemmatization also should understand what is the sentence in order to do tagging for part of speech tagging. It wants to give any sentence. So any lemmatizer tool, software tool should understand what word is that. So part of speech tagging, first of all, is essential in building lemmatizers. And last example, numerical example, which Soman explained in the last class, we saw that a verb can have a particular sentence, particular word can have different meanings. It may be used as a noun, it may be used as a verb, depending upon where it is used in the sentence. So by giving its form, either noun or verb, it is possible to reduce its lemma. Lemma means proper root word, English root word. If it is used as verb, you just specify as verb in the converter, and it will give you a lemma which is a verb. If you specify n noun, so it will give a lemma which is used a noun for the same word. So that we saw in the some examples also we saw in the last lecture. So these lectures will be made available to you in the form of videos. So once you can have, if you have forgotten, you can have more one more look at the video, and then you will understand. This was discussed in the last class by Soman. Okay, so building a lemmatrizer tool also requires POS tagging. So that is first used in NLP. Then building some kind of parsing trees. So parsing trees is what that we'll see in the next lectures. Then named entity recognition, like there are entities present in a sentence, like some may be a person, it may be a city, it may be a country, or it may be something like that, entity. So named entity recognition is also, that's what we are going to learn in the third class. So next class, so that's what is building that NER tools also you need POS tagging. And well, if you want to find out relationship, suppose there is a big sentence and the last sentence, the last few words are dependent on the first few words, and you want to build a relationship, like you want to find out relationship, which part of sentence is dependent on which part. So those kind of relationship finding in a word also require you to first do POS tagging. Once you do POS tagging, then only you can find out relationship between word of sentences, like which word of sentence is dependent on which part of sentence. So that is what so what POS tagging is a very basic building blocks. I have given you some use cases for which it is used, in which parsing of trees and building NER and named entity recognition. We'll learn in the next class. And building lemmatizer, now you understand, like if you want to derive a proper lemma of the word, like the lemma can be of same word, of lemma can be a noun, same word, lemma can be a verb. Lemma can be a verb, right? So just by specifying in the converter noun, you will get noun lemma. If you specify V, you will get verb lemma. So Soman, can you explain what is the meaning of lemma? Soman?
Sir, lemma is the root word of
Right?
any word,
which has proper meaning. Okay. And stem means just remove prefix or suffix, and whatever is remaining, whether it is having meaning or not, that is called stem. But lemma means it is a proper root word. Like if I will once again take you to this particular PPT, which has a lot of meaning. So here changes. So change, changing, changes, changed, and changer. Lemma will be change because it's the proper root word of the English. So we are reducing to a proper root word. And if we just remove the suffix ing, es, ed, and er, it will convert to chang, chang. So chang has no meaning in English, so that is called stem. It is stem. It is used. It is coming from stemming process. And lemma is change, which is coming from lemmatization process. So that is what is the difference is. So that's what I wanted to cover today, and it was a revision of this particular lecture. Then I want you to take to a proper. Now I'll want to shift to if Sauji has joined. Has Sauji joined?
Yeah, already joined.
Yeah, already joined. No, so now I'm Sauji. Welcome. You are on the right time. So now I will take you to one exercise which I'm going to give today. And for Sauji, your information, today afternoon there is no class because I need to go to airport to receive my daughter. She's coming from Ranchi, so I need to go 3:30. I have to leave for airport. So now I'll give you a small exercise based on whatever we learned earlier. So whatever demo someone gave, whatever demo, one demo I also gave. So based on those classes, I want to give a small exercise to you. So we'll quickly shift over to our Jupyter notebook. Okay. Sorry. So this is a simple example. First, we'll discuss. This example is nothing but first is we do some kind of text processing. That corpus is there, Amazon reviews, food reviews. We have some food reviews. We do some preliminary text processing to remove noise that what we learned in the last class. Noise is like exclamation, square brackets, and those kind of things we'll remove. And after that, we will do some kind of encoding using count vectorizer. So count vectorizer is a very basic vectorizer which you learn now, which you know. If you have forgotten, you have to Google it out and find out what is count vectorizer. It just counts and words and replaces the word by count in the sentence. So that is what is count vectorizer. So you have to Google it if you have forgotten. If you remember very first or second class, I covered one complete NLP example, and that's where I converted count vectorizer. So that's what this is the count vectorizer. If you have forgotten, please Google it out. And after that, once we have converted into numbers, words to numbers, we are applying a simple logistic regression model to classify whether your review is positive or negative. I think this kind of example we have seen in the past. My second class was that only. But here the only difference in the second class which we did in there was no text processing. Here we have a bit of text processing. So I'll quickly take you through the example, and then I will I'll tell you what is your exercise for today. Okay. So I think, is code visible to all? Is code visible to all? Soman, Sauji?
Yes, yes.
Code is visible, right? So here we do usual imports. So first Panda, NumPy imported. And here is only some code to see the contents of the directory. Even if you don't write, it will show you the content of the directory, like your dir command in DOS and all, na? So that ls command in Linux. So like that, it will show you the content of the directory. Even if you don't write this code, there is no harm. You will not see the content. That's all. So now we installed Word Cloud. So I'll tell you as going down the line, I'll tell you what is Word Cloud and why we have installed this particular library. So if you use exclamation pip install Word Cloud, so it will within the from the notebook, within Jupyter notebook itself, you can install a particular library. So just say pip install and library name, you will be able to install it. So that's what the pip Word Cloud we have installed. Then I have one thing I have forgotten to add here is that there is a small 2-line of code to ignore warnings. So that I have not included here. So a lot of warnings are coming. So anyway, you can find out from Google and Stack Overflow and add that code. It's not a big deal. So that is the usual code which we include in every notebook to ignore necessary Python warnings. So now we do some initial a lot of imports have been done, but all of these imports are standard taken from a different notebook, and they are not all of them are not used in this notebook, but just for the sake of completeness or whatever, cut copy and paste, I've just imported all these necessary files which you can have a look. Then after that, I'm reviewing this file. It contains the food reviews on maybe on Twitter and all. So food reviews of Amazon. So reviews are there in a CSV format. So I'm reading it. Reviews for the directory. This is downloaded from Kaggle, and it is stored in the same directory as my notebook. So it is in this form. So you can see, like I'm putting here only one sentence, so that you can see here, like head only one I am putting. So that you see here, a minute. It is running, so let us wait for a minute. It's a big file. See, so now different fields you can notice: ID, product ID, user ID, profile name. Then there is something called helpfulness number. Then there is something called helpfulness denominator. Then score. Score is the main thing, which is our y vector. dependent vector. So score is given from 1 to 5. So up to 3 we are considering that bad review, up to 3 bad review, and if 4 and 5 is given, we are considering it a 1. So up to 3 we are converting into 0, and 4 and 5 we are converting to 1. So that's how we are getting our binary dependent vector. So this is time. Summary. So summary is again about the topic of the and then text, proper text of that proper text. So this is what we have done. We have done a describe on that. So just for academic interest, we are describing the numerical variables, numerical features we are describing. So these are the numerical features, 4 numerical features. So you will get count, mean, standard deviation, minimum 25, 50 percentile, 75 percentile, maximum. So these, I think, describe, you are very well aware by this time. It will give you our basic statistical parameter about only numerical variable. It will ignore categorical variable. So now we are doing some part of data processing. So here this function is written to remove HTML. So this function we see it. So you saw yesterday also where someone explained. So we are using a library called Beautiful Soup to remove the HTML tags. Okay, so we are so once we run this function, whatever HTML tags are present in the our review text, they will be removed. So then we are removing square brackets. Here, then you are removing square brackets by this function, and then after that we are removing URLs. So all these functions we have seen in detail in last class, in which someone explained a very detailed file where a lot of text processing was done. So you should refer to that video. And once there is a master function which called denoise text, in which we called this function, like whatever functions we have written, script HTML, and remove between the brackets, we call it, and we get the pure text. So all denoise text means this text will not have any HTML tags, and it will not have any square brackets, and it will not have any URLs. So once these 3 things are getting removed, and after that we are calling this function. Okay, so this is the df.text is the column where our reviews are stored, and dot apply means we are applying denoise text function. This denoise text function which we have written, which calls our smaller functions like strip HTML and remove between square brackets, these 2. So it is a master function, like denoise text is a master function, which calls other 2 smaller functions. So we apply this denoise text to each and every row we apply dot apply means on each and every row it will apply denoise text. Means what it will do, it will take the text, it will remove the square bracket, it will remove URL, and it will remove all the HTML text. Only this much processing we have done here. Okay, so we have not removed any exclamations, we have not removed any stop words. So those kind of things, if you want, you can pick up those functions from better processing. You can do better processing. You can pick up those functions, ready-made functions from whatever we explained in the last class. We pick up that function, apply here, and do a better job of text processing. So here you can see that very basic and quick and dirty job has been done. This is not a complete job, but some kind of basic text processing is done. You can choose to find out more functions from in the last file which we just shared in the last class. You pick up those functions and you can apply them here to do a proper text processing job. Once you get the processed text, then you go ahead. Then now we are just plotting a heat map. Heat map is, I think you are all aware about heat map. So all numerical variable correlation has been plotted. It is just for academic interest. It is not making much sense. I will just make it small so that you can see it in one screen. Okay, so you can see it in one screen. See, so it is just for academic interest, not much meaning for this analysis. So you can see that this reddish, as it is going red, means correlation is going towards 1. So these red ones are very highly correlated fields. So this helpless number and denominator, helpfulness numerator, helpfulness denominator are very, very closely related fields to each other. and then score is related with score. Score is related with score. So obviously it will be 1 only. But but these are this which bigger red patch which we see here are carrying some information for us, like numerical helplessness, helpfulness numerator is very highly correlated with helpfulness denominator, and vice versa, like helpfulness denominator is also very highly correlated with helpfulness. So anyway, these variables are not useful in our analysis. So in next step, we are dropping these variables. So this is another code of dropping a particular column. So if you write delete, delete, data frame name, and then specify column name, it will delete that column from that data frame. So this is another way of, you are aware that dot drop method, I think you are already aware, but this is another way of removing column in the in Python. So we are removing ID, time, user ID, product ID, helpfulness numerator, helpfulness denominator. So these are 6 columns we have dropped now. So now if you see head, only we are left with profile name, score, summary, and text. So after that, if you notice, profile name, summary, and text are having some kind of text only. So they are all having some kind of sentences. So next step, we combine them. So text, df text column, space, plus df summary column, space, plus df profile name. So we have combined profile name, summary, and text into one. So we have done, we have combined them, and after that we have deleted a summary and the profile name. So summary and profile name we have deleted, and in the text we have combined all three. So we have all the information. Now we have only two. If you see the head, you have only two fields available, which are text is what you have to analyze, in which three fields are combined, and score is from 1 to 5. So in the next step, what you do, as I said, 1 to 3 is 1 to 3 we are considering as bad review. So for any number from 1 to 3 we are assigning 0, and any number 4 and 5 is we are assigning as 1. So we are converting it into a binary variable 0 and 1. So the next it is binary variable. So a function, simple function is written here. Again, small apply we are doing and converting into a binary variable. So now our problem is now our data set is greatly simplified. We have y, which is 1010 binary variable, 1010 y, and text, which is a combination of all the three text column in our data field combined into one. And we did little bit of cleaning on that. If you want, you can do more cleaning, like you can analyze it more. And if required, better to remove stop words and all. I can see some stop words up there, is, of, the, I, for, the, you. So these kind of stop words you can remove. Function is already given in whatever we did data processing class, data pre-processing class. A lot of functions were given. So from that, one of the function is to remove stop words. So just like we applied here, these two functions, is remove square brackets and remove strip HTML, you can apply one more function. Just type this one more function here, call this function in noise text, and you can choose to apply many more functions you can apply in text processing, whatever you want. Okay. So as I said, we have not done a complete good work of data pre-processing. We have done only quick and dirty work. Okay, to keep analysis short. So now we are observing and just finding out how many nulls. So two fields have null, like summary has null, and so I'm not sure why df we are doing and not df. So df should have only two fields, right? Score and text. So there is some challenge here because we dropped these fields earlier, right? So they are appearing here. So ideally there should be only score and text fields, right? Because we have only two fields here. So there is some challenge here actually. So let us ignore that. So whatever, let us ignore this line of text for now. So like just I'm not running it to save the time. But if you run this file again, you will get only two fields, like which one is score, one is text. Because already we have processed it earlier. So df should have only two columns, score and text. So I think this command was given earlier to processing. So that's why it is containing all the fields. So let us ignore that for now. Please ignore that for now. But you see what there are only two fields here now, score and text. So whatever blanks you find, it is replaced by fill NA method. Fill NA means whatever blanks are there, we are replacing it by only nothing, like we are just leaving it blank. And in place is equal to true means then there and there itself we are making the changes permanent. So now here we are removing the stop words now. So see, we are taking first stop words from English. Stop words was imported here. I will show you. Stop words was imported earlier. Like if I show you stop words, see, stop word was from NLTK, it was imported here. From NLTK, we imported stop words. Okay. So we imported it first, stop words. Then we want stop words for English, so specified English. Then in punctuation. So punctuation, string dot punctuation means a string function is there, and in that if you do dot punctuation, it will give all the punctuation which are commonly used in English language. So if you want, you can just print this punctuation to see what kind of punctuations it has given. Just put a print statement here and just check for yourself that what kind of punctuation it has written. So we'll get all the English punctuations. So whatever stop words we did first stop words. This stop object contains all the stop words of English. Then we got in this punctuation object, we got all the punctuations. Now we are doing stop dot update punctuation means whatever punctuations are there, now they are updated in stop object. Means now stop object contains two things. One is English stop words and punctuation. Both are there in the stop object itself. Now we are using a Porter stemmer here. So again, we are doing some kind of quick and dirty job. If you want, you can use proper lemmatization. And lemmatization function was also given to you in the text pre-processing code file that was shared with you. That function you can use. So instead of stemming, you can choose to do lemmatization here. So right now we are proceeding with stemming, and so you see the stem. We are writing a function. We are passing some text. Then we are declaring final text as a blank list. Then we are splitting the text with a space. And for every word you see, we are first converting it to lower. We are converting it to lower, and we are putting a condition if not in stop. If not in stop. So if not in stop means we are filtering off whatever words are there in stop, means all the English stop words and punctuations we are filtering here. Not in stop. So we are filtering with the help of if statement. All punctuations and all stop words we are filtering here, and whatever word is remaining, we are converting into, we are finding it stem by stemmer dot stem. This was imported earlier. So we are I dot strip means we are removing if any spaces are there, and then we are appending it to final text library. So final text library, whatever will come, and then we are joining it with the help of spaces. So whatever the final text will come, it will now not contain stop word. It will have all the things converted into lower case, and it will not have any punctuations. And all the text words will be joined in the form of a single string with spaces. So you can just print this actually. You can just print the head of this. I have not done that. So whatever, see, we are applying this function here. Stem text. We're applying dot apply method. So with dot apply, we are applying it to every row of text field. So the df.text is nothing but the text column. So for text column, we are applying it. And this here you will have the complete clean text, which will not have stop word, which will not have punctuations, and all the things will be converted into lower. And apart from this process, this is also part of pre-processing. Apart from the pre-processing, some pre-processing we did here when we used noise function. We removed noise here, right? Denoise text. So some pre-processing was done here, and remaining pre-processing was done here in the stem text. So it will contain now the stem, the normalized text, all the forms of the all the transformation of the word will be converted into stem, proper stem, English stem. So this, I think that is this till this stage we get a proper, very pretty decent kind of text processing we have done. So now we print something called word cloud. So I explained you, we had installed word cloud library earlier. Now we are we're plotting some kind of cloud, word cloud. So it is very much like our clouds which exists in the sky. So now we are plotting. See what cloud we are making. Text with weighted and average review. So we are now making a cloud of words which are forming bad or average reviews, because 1, 2, 3 we have classified as 0, right? So bad or average review all combined into one. So we are doing a cloud of words which contains only bad words, like bad reviews. So like this is the cloud. It is very much like your very much like your cloud which is there in the sky. So if you see one product, taste, coffee, Amazon, so these are the prominent word in bad reviews. So these are very prominent words, like they are repeated a lot of times. So based on their repeated frequency, the size is small or big. So if frequency size, repetition frequency is more, the it is more. So product and taste word are used very highly. They are a lot of time they have used. So maybe a lot of reviews people didn't like the taste. But see, these are the words which are forming good bad reviews. So similarly, we did a word cloud. So maximum 3000 word width of the cloud, height of the cloud we have given. Then generate, and this is the standard code of plotting the word cloud. So these are the reviews which are giving good reviews. So love word, then recommended, highly. See, people are like, see, stemma highly. Highly is not having any English meaning, but our stemmer has done it highly. So if you want to have used lematizer instead, you might have got a proper word, HIGHLY. But here there is highly word, then grocery, store, great, product. So these are the very frequently repeated word in positive reviews. So this is just a way to visualize your data, what kind of data you have. So then usually we divide it into data into, so now we have text corpus, right? In this df.text which I have highlighted, you have the complete text corpus. So till now, if you have anybody questions, any questions here till here? Dr. Shailesh or anyone? Just we have done some data processing, and we did a couple of word clouds. So very simple things, but I have spoken a lot, so it might look a bit complicated, but if you will look at the code, it is pretty simple and straightforward code. So Dr. Shailesh, Soman, Himanshu, any?
It is able to read the words within the image also, this library?
Which image? Yeah, there is no image here.
The dog, food, taste, great.
No. These are all text here. This is all text in the form of like this. This is the text. And what it is doing is, if dog, so why dog is coming bigger? Why dog is coming bigger? Because dog is.
This is image, right? See, if you see the output, matplotlib.image.access image.
No,
Image, right?
this output word cloud is the form of word cloud is in the form of image.
Okay.
So that's what we are plotting. We are looking. We are seeing the image here. Image show. So word plotlib, this is a image object. But whatever we are converting into image is dot text. So see dot text. So this dot text is the form of proper text only. See here, text. So if it is more frequently repeated, then it is size is big. Understood? And final output of this word cloud is a image. So that's why we are using a image show method here. Got it? So that's what we are not reading from image. We are reading from proper text and finding the frequency of the word. If frequency is more, word cloud also its size is more. So word cloud comes in the form of an image. So that image we are plotting here. So any other question? Is it understood, Sauji? Any other questions, Dr. Shailesh or anybody else?
No.
So now after that it is pretty straightforward. I break into train and test. Then how did I do a count vectorizer? You know why count vectorizer is used, because till this stage also in train and test we have all the data in the form of, see, in y there is all 0 and 1, so we need not convert y into numerical because it is already numeric 0 and 1. But x train and x test contains what? It contains your words in the form of the text string. So it is all categorical data. So you need to convert it into count vectorizer. So you instantiate count vectorizer, and these variables, the parameters which we are passing to count vectorizer. So I will suggest you not to give much attention to it at this stage because they are all related to word frequency. And in coming classes, you will understand it better. That time we'll come back to this. And that time you will understand it better. What is the meaning of min df, max df, n-gram. So all this will convert in the later classes. So till now, you better understand that just they are given some parameters here. Or if you prefer, just don't give any parameter. Call it with call count vectorizer without any parameter. Everything default. So like that also you call count vectorizer, like if you wish. Like that also you can call it. It will also work. Okay. So this meaning of these particular parameters I will explain you in later classes, which when you will discuss word frequency, n-gram model. So that time these things will be better clear to you. Then fit and transform we are doing on trained data. Then we are doing transform on test data. Then we view the shape. So bag of words, we get the different words. So it's a pretty huge bag of words. Like you can see the size, it is in millions. So we have millions of words. So see, what is the, you can imagine the size of matrix. So matrix is around 42, 4,26,340. So 426,340 are the number of rows in the matrix. And number of columns are 1.9 million columns. See, million, right? So it is 1.9 million column. And test also 142,000 to 114. So 1,42,114 number of rows. And columns are this many. So this is a huge vector to process for any normal machine. So, and that's why we use word vector with the help of word2vec. So in the last class we discussed word2vec. So word2vec size will be number of rows may be 426,000. Number of rows will remain same, but number of columns will reduce to 3,000 because 300. Because in word2vec model, each word is represented by only 300 or 400 or whatever you limit it to. So suppose if you limit it to 300 column, 300 elements, so the word column will size only will be 300. Here your column size is bag of word is 1.9 million. So each gigatic. So this kind of analysis we are doing here is feasible only for smaller data sets. It is not feasible for bigger data set. See, for a smaller data set itself, you have this kind of matrix size to process. So in kind of if your millions of words if you have in your text corpus, then this is not the feasible analysis. Invariably, you have to use word2vec. Okay. Then we call logistic regression. I'm not explaining logistic regression. We are using L2 penalty, iterations 500. And then C1 means what is the severity of L2, like how much penalty we have to use. So how much of that? So 1 means if it is C small means more regularization. So here we are using more regularization. Random set, you know, we use it for repeatability. So then we fit it, then print logistic regression. Then once you fit it, then you can do some kind of predictions. Then we have prediction, and then once you have predicted the score, with the ground truth is also available with us. Y-test is also available with us. Now this is the predicted. So you compare ground truth with the predicted values, you get accuracy as 79%, and then after that usual classification report, which is done on every classification model, is printed, which if you want, I can share an article with you how to interpret this classification report. Okay. I share one article with you how to interpret this classification report. So these are all covered in basic machine learning. I'm not repeating. So this is the pretty much all the analysis, what basic analysis, and limitation of this analysis is evident from the matrix size which are generated here. So this is the limitation of this kind of analysis by using count vectorizer. And that is why you have to use word vectors, word to vec, glow, those kind of transformation. You have to use that. This is the reason you have to, that will reduce, drastically reduce the number of column only to 300. So that's why you have to invariably, if the corpus is large, invariably you have to use word to vec or glow. So now, one thing I will take a pause here, and I will request everybody to be ready with pen and copy, pen and pencil. So be ready with pen and pencil, because I'm going to tell you what kind of homework you have to do. I'm asking you to replace only 10 or 15 lines of code out of this and repeat the same analysis. Okay. So any questions, Sauji, Dr. Shailesh, Shoman, and Himanshu? Anybody else? Any questions? It was a pretty straightforward analysis, but I spoke more, no? So that's why you might have felt that it is complicated. But if you look at the 8 code, all of this we already covered earlier. And it's very simple analysis actually. It's a very straightforward analysis. Sauji, any question? You are telling something. Sauji?
No. I told no question.
No. And Dr. Shailesh?
No.
So this is one complete end-to-end NLP in which what we are doing, we are first training our model with this X and Y, and after that we are predicting that after in the prediction we are passing only the text and predicting the score, whether it is 1 or 0, positive or negative. That's what we are doing. So that's why we are using logistic regression, but if you want, you can use some other classification algorithm like LSTM or a random forest or whatever classification algorithm you want to use here, you can use it. So if no questions, then I will take you to the assignment part. See, it is a very simple assignment which I want you to finish today itself in any case. See here, concentrate on this part. So what we are doing here, we are using count vectorizer. Why we are using count vectorizer? Count vectorizer we are using to convert our word. So till now here is a text, xtrain and xtest. They are in the form of text, strings. See here, text as it is text, df text. So df text, if you see plotted, df text was printed here. Df text was printed, so it is in this form, right? So same we are splitting into train and test, right? So we are splitting it into train and test. So train and test, I think by default we are not given any test like how much to be taken. So most probably 80% will be train and 20% will be test. So because that test size we have not given here, that parameter, so by default most probably it will pick up 80% as train and remaining as test. So that's what. So till this form, x train and x test contain only text variables. So I share this file with you. If you want to, like, you are not still convinced, you can print and see what form x train and x test. So now we have to convert it into vector form. Vector form means numeric form before we can put into logistic model. So what we have done? So we have used this simple count vectorizer. So as I said, you are not happy with this particular parameter, just remove and just call it black. Or for now, ignore this, call it with these parameters and ignore it. I'll explain you later. Then fit transform on train data and only transform on test data. So we never do fit and transform on text data. I think these things are clear to you. Like fit and transform we do only on train data. But in test, we usually do only transform. Why? Because the fit thing, when we do fit, so this is a combination of fit method and transform method. So fit, when we do, it learns a lot of parameters from the train data. So if we do same fit transform on trace data, your model will learn a lot of parameters from test data also, which we don't want. So we want our model to run from fit and apply it on test, because we want our test data to be totally unknown to our model. We want to keep it reserved for testing. So we never do fit transform on test. We do only transform on the test. So that's what these are basic things. So we got this kind of bag of words. Okay, so this is the limiting factor of this particular analysis, that we have huge and gigantic kind of matrix. So this is a vector size, right? So 426,340. This many rows. So each row is a vector which is representing one sentence. So each sentence is converted into 1.9 million 1.9 million 1.9 million bag of words. See here, both the train and test bag of words. First bag of word is formed, and in which after that whatever word exists from that bag of word, the frequency has increased. So I think I explained you bag of words and count vectorizer. If you are not clear, I will request you to Google once again to know how count vectorizer works. So now what I want is this. Count vectorizer, I want you to don't use count vectorizer. Instead, just go to this particular example which we did in the last class, which I also explained, and after that someone also explained. POS tagging, we did this. I shared this file. I will today also I'll share with this file with you. So just share word to vec. I want you to use word to vec. See here. So word to vec, import first word to vec. So you will need this. You will need this. This should be there in your same directory as you are storing in the Python. I will request you to store these two Python notebook files in the same directory. In the same directory, you should have this particular thing, because this content, this is what word to vec. Word to vec, all the treasure of word to vec is here in this. It's a huge file in GBs. So you should have in the same directory. So first, then you have to load word to vec. Word to vec, you have to load like this in binary form, and then you have to convert it. You have to use embedded size tag 300 only. Then use vocabulary size as you have to tokenize. So word tokenize, like whatever tokenizer he has used. So first step you have to do is tokenize. Okay. So tokenize means 8, 9, and first. So word tokenizer is imported. See here, word tokenizer is imported, and then it is text to word sequences, text to sequences, and X. X is nothing but your text data, X variable. So train you have to pass separately, and test you have to pass separately. So in this format, convert train and test into X train encoded, X test encoded. You have to convert, and Y you need not convert because it is already in the 0 and 1 form. Y you need not touch. But in this form fashion, you will use this code to convert in this form, tokenizer form, and then for that you have to import this tokenizer first. So have a look at this file, whatever he has done to import tokenizer and this Google file, you also do the same, and tokenizer word index joy, then wait a minute, tokenizer index, then take you to the next step, how he has converted here. So see, you have to declare a NP of 0. This also you have to do. Same step you have to repeat. And then word to ID. In this way you are converting. This complete thing you have to do. Whatever I have thing here. You have to understand the code, and you have to convert into word embeddings. So in that way you will get your weights in embedding matrix. Get your weights in embedding matrix, and once you have the embedding matrix, that means you have converted all the words into proper text, and then apply logistic regression on that. Understood? Na? So then apply logistic regression on that. So I want you to have 426,000 rows in train and 142,000 rows in test. This will remain unchanged, but this will reduce to 300 and this will also reduce to 300 or something similar. Okay, so you do some jugglery and then you apply logistic and see what is the kind of result you get.
So one question on this.
Yeah.
Actually, you mentioned that Google directory or whatever is bean is there, no, it should be there in the same directory. So
Yeah.
using the Google this Colab Pro, no. So last time when we imported the Kaggle database, then we used some JSON thing. So how that, because
That I think then you have to upload that also in Colab Pro, so that someone will take a small class for you, like how to upload this particular directory, how to load this into Google. So for that, I'll ask someone to give you some notes. Okay, so we'll take a small class and I will explain you how to load this in Google. Okay. So that someone will explain you. Then I want you to use like word to vec kind of thing rather than see. Yes, Sauji.
No, I am not telling anything.
So I am still not sure how you will do with word to vec. So if you want to do it word to vec, then each word will be each word. Okay, so I'll before you start, you try yourself, and in which I will brainstorm and give you more hints. I think you need more hints before you can use word to vec or to converting this. So, but something similar we want to do, and we'll have a quick class to give you more hints before you attempt this. So, meanwhile, you can study these two files. I'll share these two files with you. You can just study them, and I'll give you more hints because even I am having a little challenge here. See, here, suppose you are having xtrain. So xtrain, one row of xtrain is nothing but a sentence. And if you convert one sentence into, so that is sentence means it is one row and one single dimension vector, a row vector. Okay. So each word, if you convert into one word embedding, each word will be around 300. So it will become your vector. This vector will become 3-dimension vector. So first will be your number of rows. Second will be your number of words in the sentence. Like you have to limit each word and do the padding. And this will be your number of sequence length. And then third dimension will be your 300. Third dimension will be 300. So how you will handle it is something which is remains a question, because that is nothing that how you will handle with logistic regression is a question. So even I want to do some brainstorming. So before you use that, what you have to do, I know. I will tell you. This X train and Y train, you have to limit the sequence length up to 100 or 150 words. Rest you have to truncate. Okay. So rest all you truncate. So your sequence length will be 100 or 150. Suppose your sequence length of each sequence is say 100, and if it is less, then you pad it by 0 in before it. So this particular dimension, this row number of row will remain as it is, because row entries will not change. Your column entries here you will get 100 because you are limiting your 100 to 100 words. So for one word, each feature. So 100 columns will be there. Here also you will have 100 columns because you are limiting each word to 100. And then after that, then each word you have 300 vector. 300 representing 300 from word to word. So this 300 vector will come here, comma 300. So it will become a 3-dimension matrix. So how to handle that? So let me give a thought and then I will come with your solution. So it will become a 3-dimension matrix here. So right now it is 2-dimension because we are forming a bag of words. So it is just a 2-dimension. So if I use word to vec, it will become 3-dimension. So how to handle that? I need to give a thought, and then I will come back to you on this. Okay. So for today, I think we are done.